Okay, please, Anna, go ahead.
Okay. Hi, everyone. So, let's start. First of all, for those of you who don't know me, I'm Anna. I come from Italy. I have both a bachelor and a master degree in mathematics at the University of Florence. And then in 2021, I moved to Lucca, where I'm doing my PhD in complex networks under the supervision of Tiziano Squartini and Gallo Schelli. And hopefully in autumn, I will present my thesis, and the talk of today will focus on the papers, on the works that will compose my thesis. So it will be about the statistical mechanics of sign networks. As we know, we can use network theory. Network theory provides us a powerful framework for modeling, analyzing, understanding, predicting the behavior of many real-world systems. And depending on which kind of information we have about the systems, we can choose different kind of network structures. Undirected, directed ones, if we want to add the information about the directionality, weighted networks, if we have also the information about the strength of the interactions, or we can change also the topology of the network and considering something different, such as bipartite networks. Actually, there is another piece of information that we can add, and we can do this by considering the class of sign networks. So those kind of networks in which the edge set can be split in two subsets, the one of the negative connections and the one of the positive connections. Of course, a positive edge models a relationship that is positive, such as friendship, an ally, trust, so on and so forth. Vice versa, a negative edge models a negative interaction, so envy, distrust, a war, and so on and so forth. In the real world, there are many systems from different domains that we can model through the use of sign networks. For instance, in this slide, there are three examples. The first one comes from a social political domain, that is the US Congress. The second one comes from a biological domain. It is the Escherichia-Coli network, in which nodes are protein. A positive edge means that there is an activation between the two proteins, while a negative edge means that there is an inhibition between them. The last example is an example of a bipartite sign network. In a layer, we have the editors of the scientific journals. And on the opposite layer, there are our paper that can be either rejected. So in that case, we have a negative link, or accepted, so we have a positive link. When we study real-world systems that can be modeled through the use of networks, actually, these kind of structures are complex networks in the sense that they present non-trivial topological properties, heterogeneous structures, and so on and so forth. So if we want to study, to analyze, to predict the behavior of these non-trivial structures, what we need is a proper set of explanatory null models. And some principles coming from the theory of statistical physics help us to define, to introduce this kind of explanatory and null models. In the first part of my talk, I will introduce you these null models. So coming from the theory of statistical physics. Then I will show you how we have extended, together also with Renaud, this framework to the class of sign networks. And I will show you how we decided to employ such null models in the analysis and the study of real-world sign networks. And in the last part, I will focus on a very recent work that I have submitted like 10 days ago, together with Fabio Saracco and Tiziano Squartini. And in this case, this work is about the study of bipartite sign networks. Okay, so let's start with the first part. A very well-known principle in statistical mechanics and statistical physics is the maximum entropy principles, according to which the least biased description of a system is given by the probability distribution that maximizes the Shannon entropy when we have enforced a set of constraints. This probability distribution in statistical mechanics is known as Boltzmann distribution. This Boltzmann distribution in network theory is commonly known as exponential random graph. So let's see how the maximum entropy principle works in network theory. Assume to have a real-world system G star and to know about this system a set of empirical constraints C star. Then, if we employ the maximum entropy principle, we find that the best probabilistic description of G star is provided by the probability distribution that you can read on the slide, which has this exponential form. That is that probability distribution maximizing the Shannon entropy, which has this exponential form, under the set of constraints given by C star. And in particular, as I will show you in the next slides, these constraints can be hard or soft. The strength of such a probabilistic distribution is the fact that at the end, it turns out to be maximally non-committal with respect to missing information. Thanks to this probabilistic distribution, we succeed so to reconstruct an ensemble of statistical networks, an ensemble of networks. This ensemble, okay, in this slide you can see a graphical representation of how of the workflow characterizing the exponential random graph models. So we start from an empirical network. We assume to know a set of constraints, a set of properties about this structure, such as the degree sequence, and then applying the maximum entropy principles and solving this optimization problem related to the Shannon entropy, we find an ensemble of networks. Okay. The ensemble that we can find can be canonical or microcanonical. If we impose hard constraints, at the end we find the so-called microcanonical ensemble of networks. And in this case, the ensemble contains all those networks which preserve exactly the constraints that we have imposed. So for instance, if we have imposed the overall number of edges of the network, at the end, if we impose the hard constraints, we find an ensemble in which each graph has the same exact number of edges. Vice versa, if we impose soft constraints, at the end, we find an ensemble of networks in which each of them preserve on average the constraint that we have imposed. In the first case, so when we impose hard constraints, the probability distribution over the ensemble is equal. Otherwise, it has the exponential form that we have seen in the previous slide. Okay. When we impose constraints, we can choose to impose either global or local constraints. If we impose a set of global constraints, such as the overall number of edges of the network, for instance, then what we define is a set of homogeneous null models. Homogeneous because they do not take into account the heterogeneity of the network structure. The strength of these null models is the fact that they can be solved analytically. Vice versa, if we impose a set of local constraints, such as the degree sequence of the network, at the end we find the heterogeneous null models. In this case, they are said to be heterogeneous because they are induced by imposing a set of either nodes or edge-specific properties, and so they succeed to take into account the heterogeneity of the network structure. This second class of null models cannot be solved analytically, but only numerically. And some years ago, in 2021, some colleagues of mine at the IMT have released a powerful toolbox for Python that is available on GitHub under the name Entropy, in which you can find many numerical routines for solving the exponential random graph models for the undirected, directed, bipartite, weighted networks, and so on and so forth. Okay, after this introduction, this overview about the framework of the exponential random graph models, let's see how we have extended such a framework to the class of sign networks, and let's see how we have decided to employ these null models. Okay, in this slide and in the next ones, I will show you the null models that we have defined for binary, undirected, and directed sign networks. For both of them, we have defined both homogeneous null models and heterogeneous ones. In this slide, you can see the two homogeneous benchmarks that we have defined for the class of binary undirected sign networks, and they are the sign random graph model and the sign random graph model with the fixed topology. Both of them are induced by imposing a set of global constraints, which in this case are given by the overall number of positive edges of the network and the overall number of negative edges of the network. H of G here and in the next slides denotes the Hamiltonian function of the problem that we have to introduce to define the optimization problem related to the Shannon entropy, while alpha and beta are two Lagrange multipliers that we need to introduce to solve the optimization problem. The difference between these two homogeneous benchmarks is the fact that in this second case, together with the assumption to know in advance the overall number of positive and negative edges, we also assume to know the unsigned structure of the network. So basically, at the end, what we find in this second case is an ensemble of networks in which each of them has the same unsigned structure, the same topology, and they differ one from each other only for the distribution of the signs over the edges. So, of course, the cardinality of this second ensemble is smaller than the cardinality of the first one. Then we have defined two heterogeneous benchmarks for the class of binary undirected sign networks, which are the sign configuration model and the corresponding variant, once again, with the fixed topology. In this case, they are said to be heterogeneous because they are induced by imposing a set of local constraints, which are the positive degree sequence and the negative degree sequence. Intuitively, of course, the positive degree represents the number of friends of such a node, while the negative degree returns the number of enemies of such a node. Then we have done similar work for the class of binary directed sign networks. So we have introduced two homogeneous benchmarks, the sign directed random graph model and the corresponding variant with fixed topology, and two heterogeneous benchmarks, the sign-directed configuration model and the corresponding variant with fixed topology. In this case, the local constraints that we have imposed and that lead to the definition of such null models are both the positive and the negative in and out degree sequences. Of course, as in the unsigned case, also in the signed setting, the heterogeneous benchmarks can be solved only numerically. And we have released this software package for MATLAB that is called Simona, that stands for Signed Models for Network Analysis, in which you can find some numerical routines for solving the null models for signed networks. You can find the routines for both the undirected and directed networks and also for the bipartite ones. Okay, so let's see how we have employed these null models. From a historical perspective, the interest on signed networks comes from the formulation of the balance theory. That is a very famous social theory, according to which social agents tend to interact between each other in such a way to minimize the frustration of the environment in which they live, in which they work, and so on and so forth. Okay, so our goal was to test the validity of such a theory in a real-world signed network. If one wants to test the validity of a theory, of a social theory, as in our case, there are three main ingredients that we need. The first one is a proper representation of social networks. The second one is a proper definition of frustration. And the third one is a proper set of null models that we use to quantify the statistical significance of such a frustration. Regarding the first and the third ingredient, we have already them. Of course, signed networks provide a powerful, signed network provides a powerful tool to represent social environments, social networks. And of course, we have the exponential random graph models for the signed case. The missing ingredient is a proper definition of a frustration. And it depends, of course, the definition of frustration is based on the principles given by the balance theory. But from a geometrical perspective, let's say, it depends on which kind of network structures you are considering, for instance, undirected or directed, and also on the perspective that you are adopting, for instance, microscale or mesoscale perspective. Okay. Now, first of all, I will show you the results related to the analysis of undirected signed network. In this case, the definition of frustration that we consider is based on the abundance of triangular motifs. And this because the principles of the balance theory can be summarized by the two informal principles: a friend of a friend is my friend, and an enemy of my friend is my enemy. So basically, if we translate such principles into triangular terms, the balance theory, actually the strong balance theory, that is the original version of the balance theory, prescribes that the triangles with an even number of negative edges are a signature of balance. Vice versa, those triangles with an odd number of negative edges are a signature of frustration. Later, in the 50s, Cartwright proposed a new version of the balance theory that is known as weak balance theory. In this case, also the triangle with three negative edges is considered as balanced, because basically the idea is that we can see each node, in this case A, B, and C, as forming a group on its own. And so it's not frustrating to think about their enemies between each other. Okay, so now we have this definition of frustration based on the abundance of a certain type of triangles. Now, if we want to understand if real-world sign networks tend to support or not such statements, such definition of frustration, we have to compare the empirical abundance of triangles with the one expected under a proper null model. In order to do this, what we have to do is to consider the hypothesis that behind any real-world sign undirected configuration that we want to study, there is a probabilistic generative model. In this sense, then we can expect some degree of statistical noise affecting the configuration, the network structure that we are studying. Okay, so let's see some results. Okay, before there is another ingredient that we need, that is a proper statistical measure, and we employ the zeta score, which returns the number of standard deviations by which the empirical number of a certain type of triangles differ from the one expected under the null model. A positive zeta score means that there is an overrepresentation of that kind of triangles in the data. Vice versa, a negative zeta score means that there is an underrepresentation of the triangles in the data. In this slide and in the next one, I will show you the results related to a massive multiplayer online game that in principle, it is a directed dataset that we have undirectorized by a simple recipe that you can find in our paper. Okay. In this slide, you can see the evolution of the zeta scores of 10 days of this massive multiplayer online game under our two homogeneous benchmarks, the one with free topology and the one with fixed topology. And interestingly, we can see that under the homogeneous benchmarks, the data tend to support the principles of the balance theory, and in particular, they tend to support the weak version of the balance theory. Indeed, in particular, under the fixed topological model, we can see that the only type of triangle that is underrepresented in the data is the green one, which is the only one labeled as frustrated under the weak balance theory. Vice versa, interestingly, when we change null models and we employ our heterogeneous benchmarks, once again, the data tend to support the balance theory, but in this case, they support the strong version of the balance theory. Indeed, you can see that only the red and the blue triangles are the ones that are overrepresented in the data. So it seems that the conclusions that we find strongly depend on the kind of null models that we are considering.
Can you just quickly tell us what the two different null models were? This one and the previous slide.
Yeah.
Yeah, so what was the difference between the two null models, between this slide and the next
one? These ones are the ones induced by imposing a set of global constraints. So basically, you have less control on the network structure. In this case, you have much control because they are induced by imposing the degree sequence. Okay, now let us move to the directed setting. In this case, in the undirected framework, we have considered triangles. Instead, in the directed framework, we have decided to study the concept of frustration, the notion of frustration, related to the one of reciprocity, and I recall you that in network theory with reciprocity, we mean the tendency of nodes to be reciprocally connected. So basically, the analysis of the balance of the frustration that we carry on is based on cycles of length 2. First of all, we have decided to consider only full reciprocal bias, so the cycles of length 2. And according to the principles of the balance theory, in this case, we have that the two reciprocal diads in which the two edges have the same sign represent a signature of balance, because basically the two agents agree about each other. Vice versa, the reciprocal diad in which we have a negative edge and the other one is positive returns a signature of frustration, because in this case we have another number of negative edges, and of course, intuitively, the two agents disagree about each other. Then, since many of the real data that we study are really sparse, we have decided also to consider the role played by the single diads. And in this case, we have considered both of them, so both the positive and the negative single diad, as a signature of frustration by considering the missing edge of a lack of interest in reciprocating the interaction. Once again, I will show you the results related to this massive multiplayer online game. In this case, of course, we are considering its original directed version. And I recall you that in the undirected setting, we saw different results depending on the heterogeneous or homogeneous null models. Instead, in the directed setting, the conclusions are quite different. In this slide, you can see the evolution of the t-scores under our free topology null models. So those kind of null models in which the agents, in which vertices, can choose both how to interact and with whom interact. And in this case, the data tend to support the directed version of the balance theory based on the cycles of length 2 and on the single diads. Indeed, you can see that the only two patterns to be overrepresented in the data are the blue and the purple one, which are the two considered as balanced. Vice versa, when we employ our fixed topology null models, so those kind of null models in which agents can choose only how to interact, no univocal conclusion can be found. Indeed, you can see that in this case, also the negative single diad that returns a signature of frustration is overrepresented in the data. And we have considered such a result that we found also in all the other datasets that we have studied as a signal that a study of the directed version of the balance theory based on higher order motifs, higher order properties is needed. So here there is the summary, and here there are the take-home messages about this part. So when we study the undirected design networks, homogeneous null models tend to favor the weak version of the balance theory, heterogeneous ones favor instead the strong version of the balance theory. And in particular, agents that can only choose how to interact, so under the fixed topology null models, strongly avoid engaging into frustrated relationships. Vice versa, when we consider the directed setting, we saw that the extension to the directed framework of the balance theory is not so trivial, and so we decided to start with the shortest cycles, so to study this balance related to the concept of reciprocity. And since we, under, for instance, our fixed topology null models, we didn't find univocal conclusions, we recommend to consider higher order levels in the study of the balance of frustration, and we also recommend to always consider the role played by the reciprocity. Okay, now let's move to the third part. Now I will talk about bipartite sign networks. As I was telling you at the beginning, it is a very recent work. And in this case, I recall you that with a bipartite network, we mean a structure in which, a graph in which nodes are split into subsets and into layers, and each node can interact only with nodes belonging to the opposite layer. So if we consider a bipartite network, we don't know which are the interactions among nodes belonging to the same layer. So a question that may arise is, how can we find the interaction? How can we reconstruct the interactions on the layer, or on a layer of interest? In 2017, Saracco et al. Proposed a validation scheme for the projection of unsigned bipartite networks. Together with Fabio Saracco and Tiziano, we have extended such a validation scheme to the case of bipartite signed networks. Very briefly, this validation scheme requires, first of all, the definition of the exponential random graph models for bipartite signed networks, and we have computed these null models. And once again, we have defined both heterogeneous and homogeneous null models. And in both cases, we have defined both the free topology and the fixed topology variant. And then the second step of this validation scheme prescribes to employ these null models to statistically validate the sign projection. And in particular, we have defined two variants of this projection scheme that differ one from each other for how they treat ambivalent patterns and missing ties. And in particular, they differ one from each other in the definition of, in the way in which we decide to measure the nodes similarity of the nodes belonging to the layer that we want to project. The first scheme that we define is the so-called zero-deflated projection scheme. In this case, we define the signature, so the nodes similarity, let's say, by considering only the full dyadic motifs. So V motifs, we consider in which we have two nodes belonging to the layer that we want to project, and a node that is the vertex of this V motif on the opposite layer. And we define the signature of any two nodes belonging to the layer of interest as the difference between their concordance and their discordance. The concordance is given by the overall sum of the concordant V motifs, while the discordance is given by the overall sum of the discordant V motifs. Then we have defined a second scheme that is called zero-inflated projection scheme. And in this case, the signature, so the nodes similarity, is given by, once again, the difference between the concordance and the discordance between each pair of nodes. But in this case, the concordance also considers the role played by the empty V motifs by considering the lack of interest in pointing the item in the opposite layer as a signal of concordance, while the discordance is given by the overall sum of the discordant V motifs plus the partial V motifs. Okay, now we have in mind these two schemes that and they are different for the definition of the signature of the node similarity. So let's see how which are the main steps of our statistically validated validation scheme. The first step prescribes to consider each pair of nodes belonging to the layer of interest, so to the layer on which we want to consider the projection. And for each pair of nodes, we have to consider to measure their similarity, their signature. So we have to decide if we want to employ the zero-deflated or the zero-inflated projection scheme. Then we have to quantify the statistical significance of the measured similarity between these two nodes. So basically, we employ our exponential random graph models and we compute a p-value. If we decide to follow the rules, the idea of the zero-deflated projection scheme, then we will employ null models with fixed topology. Vice versa, if we adopt the zero-inflated projection scheme, the null models that we use are the ones with free topology. Then we repeat the steps A and B for each pair of nodes belonging to the layer of interest. And once we have completed step C, then we find we have a matrix of p-values. And then considering this matrix, we apply a multiple hypothesis testing procedure in order to find which are the pair of nodes that are significantly similar. And this multiple hypothesis test that we employ is the false discovery rate. Okay. In this slide, there is like a graphical representation of our inference scheme. The first question that we want to answer is the one that is the empirical value of the signature significantly different from the one expected under the chosen null model? So basically, we have to reconstruct the distribution of the signature and to evaluate the p-value of the signature between any two nodes. Then, since we are considering signed quantities, and since the signature can be both positive, can be both a positive or a negative value, we have to consider a two-sided test of hypothesis. And basically, we will say that the deviation from the expected value of the empirical signature is negative if the similarity turns out to be significantly smaller than the one expected. So in this case, we will have a p-value in the left tail of the distribution, so in the red zone, and the two nodes will be two candidates to be connected by a negative link in the projection. Vice versa, if the deviation is positive, so say if the signature, if the node similarity is higher than the one expected under the null model, we will be on the right tail of the distribution, and so the two nodes will be two candidates to be connected by a positive link. Okay, once we find our monopartite projection, we decided to analyze the macro scale organization of this monopartite projection. And we do this by adopting an agnostic attitude that is the one that we have proposed together with Diego and Tiziano in the fourth paper of my thesis that today I'm not presenting. And this agnostic attitude prescribes to employ the Bayesian information criterion and to minimize it. The Bayesian information criterion is the right approximation of the minimum description length when the number of parameters that we want to estimate is finite, as in our case. And the likelihood that is involved in the Bayesian information criterion is the one of the stochastic block model that, of course, we have computed for the sign setting, always in the framework of the exponential random graph models. Okay. First of all, we have tested our validation scheme on a bunch of synthetic networks. In the first row, on the top row, you can see some three adjacency matrices of bipartite sign networks. A blue dot means that there is a positive edge, a red dot means that there is a negative edge. So for instance, if we focus on this example in the first row, in the first column, we want to project the bipartite network on the layer represented by the y-axis. And in this case, we have two group of nodes. The one that goes from 0 to 35, I guess, that in which each node likes items that go from 0 to 50. Vice versa, in the second group, we have nodes in which each of them dislikes items from 50 to 100. So basically, what we expect is to have two highly connected block of nodes connected by positive links, because we have these two groups which with an high value of the concordance, and so it means that there will be a high value of the signature of the node similarity. Vice versa, since there is no clear opinion about the second part of the items, we expect to have both negative and positive edges between the two blocks, and of course with more sparseness. And our validation scheme, in this case, the validation scheme that has been employed is the zero deflated one, so the one based on the fixed topological models, and it returns what we expect. Then we have tested our method also on some real-world sign network, and you can find some results in our paper, but I decided to show you these results that I think that are quite interesting. In this case, the real-world network that we are considering is the USA House of Parliament. On the first column, you can see the results under the zero deflated scheme, and on the second row, the zero inflated scheme. So here we are considering only full dyadic motifs. Here, both the full and the partial dyadic motifs. Okay, first of all, we can see that the main difference between the two projections is the density. Of course, in this second case, since we are considering also the zeros in the adjacency matrix, we will have a denser monopartite projection. Vice versa, it will be sparser, the one given by the zero deflated scheme. Then, in order to understand which is the macro scale organization of our projection, we have minimized the Bayesian information criterion, and we can see that a non-trivial mesoscale structure can be recovered, also in the case of a very dense network. Indeed, of course, if we consider a dense unsigned network, all nodes will belong to the same community. But we have signs, and so when we have signs, we can retrieve a non-trivial mesoscale structure, also if the network is really dense. Vice versa, we have tried also to minimize F. F here is the frustration that is given by the overall number of misplaced links, that are the overall number of negative links that belong within a community, plus the overall number of positive edges between communities. And surprisingly, interestingly, we find that the minimization of F returns a different partition from the one given by the minimization of the Bayesian information criterion. And in this case, then our projection turns out to tend to satisfy the principles of the strong balance theory. Indeed, we have these two communities in which there are many positive links connected by negative links. And in this case, also under the reflected projection scheme, the community structure is different, and maybe you cannot see, but in this case, we have many little communities composed only by one or two nodes, because basically F, if it can separate nodes connected by negative links, it will separate them. And so in this case, we have many nodes that basically are nodes connected by only one negative edge, and so they are separated. Okay, so here is the end. We have proposed these two validation schemes for projecting bipartite sign networks. If you want to consider only full dyadic motifs, you have to adopt the zero deflated projection scheme. Otherwise, you have to adopt the zero inflated projection scheme. And what we have found is that non-trivial mesoscopic structures can be detected in our projections. And in particular, these non-trivial structures cannot be traced back to the constraints defining the employing benchmarks, so the heterogeneous, the homogeneous, and so on. Okay, and that's it.
Any questions in the room? If people have questions online, you can raise your hand or unmute yourself. Yeah, that's it.
All right, thank you for the very good talk and really cool topic. Can you just say again, this was a bit quick for me because I'm not in the field. Can you say again the motivation for using the Bayes information criterion for the model selection?
Yeah.
You had one slide on it, but could you just?
Yeah. Okay. There are in the sign literature many attempts to study the mesoscale structure of sign networks, and in all these attempts, the two score functions that have been employed are the sign modularity and the frustration. So the maximization of Q or the minimization of F. Both of them, if the network tends to satisfy the balance theory, so it means that if the network admits a partition of nodes in which we have positive links within communities and negative links between them, they will find this kind of partition of nodes, even if this partition does not coincide with the structural one, so with the one given by the standard definition of community structure. So dense community usually are blocks of nodes densely connected. But instead, the maximization of the modularity and the minimization of F then do not consider the density, only the role played by the signs. Instead, the Bayesian information criterion basically ignores the principles of the balance theory.
Okay.
So it succeeds to reveal, to find the real community structure according under the traditional definition. The only case in which the Bayesian information criterion considers the role played by the signs is in the dense case, as I have shown you in this case. Because in this case, the Bayesian information criterion does not return a block structure with only one community, but in this case, it isolates a highly positively connected block from the other two, for instance.
Okay.
And in particular, the Bayesian information criterion leads to be agnostic on the end. So what we say in our paper is that basically the maximization of F and the minimization of the frustration allow to answer a certain kind of a question, that is, there exists a balanced partition of the network. Vice versa, the Bayesian information criterion allows to answer a different question. So, which is the macro scale organization of the network?
Okay, cool. Thank you.
Okay.
So in the introduction, you mentioned this data set with the information about editors and papers, right? And you would expect that the motifs that you will observe in such a system are quite different from the ones here, for instance, I guess.
Yeah.
Because the reason for a negative edge is quite different.
Yeah.
Some, so like the notion that the paper is maybe incorrect or correct. And also a question of text. There are multiple reasons why you would expect to find a negative edge. And I just wonder if you tried to use your method on that data set, if it's available, or in that paper. So what are the type of like properties that observe in that data in terms of like local motifs for the sign network?
I don't know if actually exists a data set.
Okay. I thought it was like from the last paper.
Because
three references, 3 images. So I thought
it was only the image. Yeah, okay. And but of course, in this case, of course, the definition of the similarity depends also on the data set that you are employing, of course. But maybe we can check if I find something related to this data set, and I can try to test the method. Yeah, of course. Because in our paper, we have considered only the US House of Parliaments, the USA Senate, and a data set about movies. So in a layer, we have the users, and in the opposite layers, we have the films, the movies that they, yeah. But we definitely have to try our method on our type of networks.
Thanks.
I wanted to follow up on Tassilo's question about the difference between the minimizing the Bayesian information criterion and or for maximizing and minimizing the frustration. So my understanding of your explanation was that when you do the Bayesian information criterion, you also prioritize dense communities. Do you think that the communities you find with the frustration method are somehow a coarse graining of the communities you find with the Bayesian information criterion method?
It depends. I think that there is no univocal answer to this question. Yes, because for instance, in our paper, the one that I have not presented today, there are what's the reference? No. Okay, that is the second one. We saw that there are some data sets in which the topological mesoscale structure, community structure coincides with the one prescribed by the balance theory. And so in that case, we cannot talk about a coarse graining, right?
What do you mean by it coincides with?
It means that the dense block, the dense blocks of the network structure coincides with the one we have a large number of positive edges, and they are separated by negative edges. And so basically, and if such a partition exists, is the one that the maximization of the modularity or the minimization of F will find.
Okay.
If the standard community structure does not coincide, maybe with the one prescribed by the balance theory, maybe in that case.
So like in the US Congress case that
Yeah.
you showed, it doesn't coincide.
No. And actually in literature, there is another kind of balance theory that is known as relaxed balance theory, according to which also blocks with the negative edges are additive. So basically, at the end, the Bayesian information criterion helps to answer the question, is the network strongly or weakly balanced or relaxedly balanced? So does it admit both positive and negative blocks or only positive ones?
I have a couple. So first, a clarification on the free topology null models. So are those basically just stub matching procedures in the end? Like, because I guess for the fixed topology, you don't need stub matching, so you're just assigning
Exactly.
the things, but just mechanistically, it's essentially you define the stubs as negative and positive, and then you do stub matching like in a regular configuration model.
Yeah.
Okay, cool.
Yeah.
Just to clarify.
Yeah, for instance, together with our work, it has been published by Kovacs and Howe, another paper in which they define a similar null model with the fixed topology. But in that case, they define this null model in which they basically randomize the positive edges, and then the other edges are the negative ones.
Okay.
Yeah.
Yeah.
Instead, we randomize it.
That each one, Kovacs.
Yeah.
Yeah. Okay. And the other one is about the data set, the massive online one. So maybe
Yeah.
we hope we'll actually have the answer. But I was interested in the kind of monotonicity of the measures. Like, is the data set like cumulative somehow, or does it really just stabilize over time like that?
We saw these results.
Yeah, because like the patterns, like they get stronger as you go. Is that something to do with the data set or the way you've defined the network, or?
The only the fact is that more the day increases, more the density of the network, and the network becomes larger and larger.
Is that
And
because there are more interactions as time goes
Exactly.
on? But it's not cumulative. These
No,
are snapshots.
no.
Okay,
I
got
think
it.
that yes, the zeta score is sensitive to the number of interactions. Yeah.
Okay.
Yeah, small one. With the null models, with the null models that you presented, you've constrained, if you have the heterogeneous null models, you've constrained degree sequences.
Mhm.
And then you still see, for example, in these examples that there are still significant strong balance, as there's balance. So that presumably means that balance cannot be explained by degrees. Is there a way to constrain mesoscale structure? Are there null models that will constrain more things, basically, to see at what point does balance become expected, or does it stay unexpected?
From my knowledge of the literature, I don't know. I don't think that it exists, but it could be nice. So.
Yeah, because I guess it like following on to that, like part of the thing that's important for balance is triangles, right?
Yeah,
So here we're fixing the degrees, but that's like lower order than the triangles.
Yeah.
But then you have the fixed topology also. So you see what happens when you don't change the topology at all. So that starts to answer the question. But yeah, maybe if there's a way to fix triangles.
So fixing some higher order properties would be nice, and yeah, of course.
Okay, maybe sorry, like do that. Okay, to build on Tim's question, maybe so just on the plot on the right, for example, so they get bigger, like the differences get bigger and bigger. But is there a reason why they, in the beginning, they don't like cross the lines, in the beginning, and that like they never cross?
I don't know.
Okay,
I
yeah.
think that it's I don't know. I don't
Okay.
think that there is an explanation. And in this case, it's quite interesting. Also, they are quite symmetrical.
Right.
With respect to the zero line.
Yeah.
Yeah.
True.
Yeah, could you have error bars on these? No, because this is scored.
No.
So you wouldn't have error bars on top of them.
I know.
What's interesting is that the symmetric ones are complements of each other.
Yeah.
the red and the yellow are.
But actually,
opposite.
this result is only on this kind of data set. In our paper, we have considered many other data sets. And in each data set, we have found the same results about the weak and the strong version of the balance theory. The only data sets in which we found different results were the one of coming from a biological domain, but it makes sense, right? Because the balance theory has been formulated for social environments, for social networks. So it's quite fair find that biological networks tend to be totally frustrated. Yeah, totally frustrated. Yeah.
Frustrating.
Yes, there's a lot of error in those as well. That's not really accounted for. Okay, I don't see any questions online, so let's thank Anna again. See you all next week.